Hello everyone. On behalf of all the co-authors, Jack and I will be presenting our work, Are You Really Muted? A privacy analysis of mute buttons in video conference apps. This work was done in collaboration with Loyola University Chicago. Our co-authors are George K. Thiruvathukal, Neil Klingensmith, and Kassem Fawaz. Video conference apps exploded in popularity and usage during COVID-19, allowing millions of users to work from home. VCAs require access to the camera and microphone while using the application. A user is always notified when the app is using a camera, usually by a green light turning on or notification from the operating system. Microphones, on the other hand, sometimes do not have the same indicators except some Apple products. Even though mute buttons is provided to mute the microphone, there is no thorough privacy analysis of this function for VCAs. So we are here today to address the question, what about the mute button? To answer the question, we need to first establish what should be happening by asking users what they think. We need to understand the VCA's actual behavior, and from there, observe if what the user expects is actually reality. Here, let us start with the first question. What are the user's expectations of the mute button? To answer the question, we recruited more than 200 participants who worked from home during the pandemic. We expect these individuals to know meeting apps and be comfortable using them. Their opinions and expectations of the mute button are a good baseline for our discussion. On top of the mute button expectations and opinions, we also learned which apps are the most used, why normal VCA users mute their microphone, and what activities they are doing while muted. Zoom, Teams, Slack, and WebEx were unsurprisingly the most popular VCAs. As for the reasons that users choose to mute my microphone is to preserve their privacy of background activities. Those activities including watching TV, talking, cooking, listening to music, and cleaning. As we found out in our user study, the participants' expectations and assumptions were interesting. The table represents 4 possible states of a VCA. The VCA is off, the VCA is on but there is no meeting, the user is in a meeting but is muted, and the user is unmuted in a meeting. There is an obvious discontinuity of when a user believes the VCA is actually listening to the microphone. However, the participants have a clear expectation of when VCAs should be listening. They believe that VCAs should only access the microphone when they are unmuted within a meeting.
Now that we understand what the users expect, we will explore how VCAs actually work. There are 3 main challenges when doing this study. Tracing audio data within the system poses a challenge because audio data begins in an API call controlled by the operating system. All the API calls across each OS are different. Knowing where the audio comes from is only half the battle, though. We also have to watch when other applications in other memory spaces call the API functions. This is the second challenge, building a system that can directly observe which apps are looking at the microphone through the lens of the API. The final challenge was tracing the data within the application. All the VCAs use different libraries, and each come with their own unique library. Going from the API watch point into the application posed to be an especially big challenge, as the memory addresses were always changing, which made it very difficult to script. However, we were able to overcome each challenge relative to the operating system. They all required different tools and scripts, but it was possible. Windows' audio access mechanism is just simply the Windows API. We used a tool called API Monitor, which could attach itself to each unique API call. We then traced the audio bytes into the application by grabbing the audio's buffer address and following the address using x64dbg and Scala hide. macOS had a similar API system with the microphone, but Xcode's instrumentation tool is what captured the API calls instead of API Monitor. We then followed the API calls into the application using IDA Pro. Finally, in Linux, we use a tool called Dynamo Rio to capture API calls to Pulse Audio. We then follow the data into the applications using IDA Pro. Chromium, on the other hand, just required some source code editing in the right places, which are detailed in our paper. Understanding how VCAs work is not a simple task. In fact, each one works differently. So from our user study, we examined a breadth of options that were the most popular. We also need to examine their functionality over all the operating systems. What we saw was 3 characterizable behaviors. The first behavior was when an application was continuously sampling the audio buffer during the entire runtime. This includes when the software mute was engaged. This was rare, but we saw that WebEx was continuously sampling at all times. The second characterizable behavior was when the VCA had access but chose not to use it. This case is accessible but not accessed. We found that this was the common case across all the operating systems. Most VCAs who had access only used it when the software mute was disengaged. VCAs do have access to flags that notify them if there is access, as in if the audio is silent or not. These flags do not leak any raw audio bytes. This case, however, does require that the user trusts the VCA. Finally, the last case is the software mute case. This is when the user is given absolute control over which app is using the microphone. Web browsers offer this functionality when they allow for the user to software mute the VCA in the same window as the application is running in. Windows and macOS have similar functions, but the options to turn them off are located in different menus that are commonly foreign to normal users. macOS does force the user to allow the application access, whereas Windows does not. The second you launch an app in Windows, they could have access to your microphone. We want to explore the continuous case of WebEx and understand why the VCA needs to always sample the audio buffer. Our experiment setup is laid out as follows. We already have discussed how we gather information from the microphone to inside the device. But to get the full picture, we need to now know how we capture the network traffic. To do this, we capture packets using Microsoft's Network Monitor. To decrypt the packets, we use the API monitor again to attach to both the Ethernet APIs and the network encryption APIs. We found that WebEx was passing their data as plain text before the API calls. Therefore, we can get full unencrypted traffic leaving our machine. Most packets were nothing special, but we saw something interesting with the data leaving with the telemetry packets. We saw that even when muted, these telemetry values were changing, implicating that there was an audio-derived data leaving the system while the user was muted, which then brings us to the next question. Do these telemetry packets leak any private information about the user?
Here we set up an experiment to collect telemetry data and observe whether any private information can be leaked through this process. Our setup consists of two machines. One machine was a normal user with a muted microphone in a WebEx meeting, which was hosted by the other machine, who was also muted. The other machine played hours-long video consisting of single background activities. These activities are selected from our user study, and each activity consists of more than two videos. We deployed our analysis scripts with the tools discussed earlier to collect live telemetry data as the meeting was ongoing. In total, we gathered more than 180 hours of telemetry data points, which were then fed into our classifier training model. We present the data visualization of 3 audio gain values captured from the telemetry data in a figure here. Each color represents one background activity collected in our experiments. It is clear that there are noticeable clusters. In other words, we can fingerprint these background activities by the outgoing telemetry data. Based on the data we collected, we trained our 3-layer CAN classifier and achieved more than 77% accuracy on average in evaluation set 1 and 89% accuracy for set 2. In the short time since we made this work public, it has exhibited a significant impact on the research, the public, and developers. As a result of this work, we expect more software and hardware-based control mechanisms to provide users with assurance about the behavior of microphones in commercial platforms. On the public side, this work received significant media attention through platforms like the BBC, The Independent, and the Computer World. Further, this work has generated extensive online discussions on Reddit and other platforms, such as Skinner on Security and Hacker News. After our investigation, we also filed a responsible disclosure to Cisco. In response to our disclosure, Cisco released an official blog post acknowledging our results and ceasing the collection of audio telemetry information. A statement described on this site was published a few days after the release of our preprint paper. In conclusion, we first presented a user study to understand the VCA user expectations. We traced VCA apps and found WebEx sending out telemetry data, which may undermine users' privacy. However, our method cannot generalize to some apps due to their encryption before sending to OS socket API. Also, the OS level indicator cannot correctly reflect whether the VCA is actually actively reading the data from the microphone. Meanwhile, privacy policies are not explicit about data collection when a user applies the mute button. We think there should be more native support for a mute button, similar to cameras. Thank you.